So here for problem 5, it states, sketch the region R in the xy plane, bounded between the graph of y equals x to the fourth, and y equals x to the 1/2. Set up an integral that computes the area of your region, but do not evaluate this integral. So if you recall, when you were doing these area problems between two curves, the formula stated that the area A must be equal to an integral from a to b of f of x minus g of x, where basically your function f, is what we call the top function from the graph, and g of x is the bottom function because f of x is always going to be greater or equal to g of x on the closed interval a to b. So one of the first thing that you have to do is find your a and b, which is basically the point of intersection, right? So to find the point of intersection, I would have to set the two equations equal to each other, right? Since it was given that y is equal to x to the fourth and y is equal to x to the 1/2, I can definitely set these equal to each other. Now, if I want to solve for x here, and let's say I want to do this using factoring techniques, what I could do is I can somehow get rid of this 1/2 by multiplying both sides of the entire equation by 2, right? If you recall way back when you were doing probably algebra, if you have x to the power of m raised to the power of n, this is the same thing as x raised to the power of m times n, right? So if you have a base raised to a power raised to another power, you're allowed to multiply the exponents. So x to the fourth power, when we square it, that's going to become x to the 8th. And then on the other side, x to the 1/2 squared is just x, right? Because 1/2 times 2 is just 1. All right, now I can set, since they're set equal to each other, I'm just going to subtract x on both sides, right? So this gives me x to the 8th minus x equals 0. And then I can solve it by factoring. So I factor an x out. We get x to the 7th minus 1 is equal to 0. And if I split this in two equations, we get x equals 0. X to the 7th minus 1 is equal to 0. So we get one point of intersection, x equals 0. For the second point of intersection, you would have to add 1 on both sides. And then you take the square, well, not a square root, but rather a 7th root. So you take the 7th root of both sides. So the 7th root of x to the 7 is just x. The 7th root of 1 is just going to be 1. So those are my 2 point of intersection. You could have probably got these two values by just comparing your two functions and thinking about what values of x will make where they both equal at. I think you would have probably got 0 and 1 just doing a little mental math, but here I just show it. All right, so now I'm going to make my sketch. And then I'm going to write out the integral. So you have to sketch the graph, by the way. You can't go about it because it did say sketch the region of interest. So here's our y-axis. Here's our x-axis. For the graph of y equals x to the 4th, that's a power function with a degree, an even degree. So it would resemble the graph of y equals x squared. So informally, it looks like I'll be drawing a graph of a parabola, right? So here's the origin, by the way. Let's say here's x equals 1. Here's y equals 1. I'm just plotting these 2 points, use it as reference points. And I'm basically making the graph for x to the 4th power. So there you go. That's your graph. Now the graph for y equals x to the 1/2, that's just going to be the square root function. So it will look something like this. So y equals x to the 1/2, or square root of x. Now, we're trying to find this area. So between 0 to 1, you can, between x equals 0 to x equals 1, between in this interval, you can see that the square root of x is greater than y equals x to the 4th. Okay, I'll zoom in on the picture so you can see it a little better, right? You can see that that blue curve is the top curve, x to the 4th will be your bottom curve. So this will give us that the area A is simply going to be equal to the integral from 0 to 1 of the square root of x, or x to the 1/2, minus x to the 4th dx. And I have some good news for you guys, because in problem 5, it says you set up the integral, but you don't evaluate it. So we're going to leave this alone. Before I pause this video, let me just do number 6 while I'm at it, because problem number 6 states, okay, you're going to use your same graph again, and you just got to do a couple more things to it. And you want to find now the volume of that region. So what I'm going to do is just keep going just a little bit more for problem 6. So what I'll do is copy this graph. I'll make a better sketch in a moment. I still need to make like a better sketch of this so that way you guys can see it. So let me just delete what I had here. All right, so for problem 6, it stated that we wanted to set up an integral that computes the volume of the solid obtained by revolving the region R in the previous problem. So it will be the same two graphs that I'm going to draw again, but it's rotating about the x-axis. So it's rotating this way, right? That's your x-axis. So again, I just want to make a better graph of the situation. So I knew that in the previous problem, the points of intersection were the origin and 1, 1. I knew that the square root function sort of looked like that fishing hook, looks something like this in that interval. And the x to the fourth would look something like that in blue, right? So in black was the y equals square root of x. I was going to put square root of x here, and then just put x to the 4th here. All right, so when I'm rotating this around the x-axis, remember your region is going to basically reflect in the negative x-axis, right? So if you look at how the square root of x curve looks like, let's just say, with loss of generality, let's say I use this reference point 1, -1, then you'd have had this piece. And then in blue, you're reflecting that as well. So how would that look if I reflect it? Trying to figure out that part. It can't be the way that the square root of x looks like. So maybe something like this. This will be its reflection.
Yeah.
Okay. So what I did with the dotted lines is the reflection. And now what I'm going to do is basically draw somewhat of a picture. In the interval from 0 to 1, I'm just going to choose like a test value here. Let's say I use a value here. Okay, if I sort of draw my, based on the rotation, if I sort of make my drawing, it will look something like this, right? So here's one of the drawings, right? So our basically this shape here, we can have a radius. So the radius is always going to be the distance between the x-axis and one of your curves. So notice that there's going to be essentially two radius here. The outer radius is the distance from the x-axis all the way to your, depending on what your square root of x is, right? So the outer radius is going to be the square root of x, because whatever test value that I use here, the outer radius, the height basically depends on your square root function. The inner radius, on the other hand, is going to be just x to the fourth. So it will look something like this. So what I have here now, it's not the best image, only because I didn't do this to scale. Maybe if I were to do this to scale, you would see that you have your washer instead of a disc. So there's your sketch, and now you just got to use the formula for volume. So we get volume V, is equal to pi from A to B of the outer radius squared minus the inner radius squared dx. Outer radius is going to be square root of x. Inner radius is x to the fourth. So you have volume equals pi from 0 to 1 of square root of x squared minus x to the fourth squared dx. Now, because it says that you don't have to evaluate it, you're just setting it up, I think this is okay. If you do want to simplify this a little further, square root of x squared is x, and x to the fourth squared is x to the eighth. And that's problem 6.